we are now going to see the main elements of a convolutional neural network. CNN are neural networks in which convolutions are used instead of matrix products in several layers. A CNN typically includes three operations: the convolution, the activation function, and the pooling. Convolution is related to the more general idea of parameter sharing that we've seen in the first session. Parameter sharing is a type of regularization and replaces the full dense connections that are used in classical neural networks. The convolutional operator between an image I and a kernel K is defined as follows. Each component of the resulting convolution is a sum over the two dimensions of the image. The kernel K corresponds to some weights of the network that is going to be learned based on the dataset. Here is a simple example to understand convolution. To keep things simple, let us consider an image in black and white. Pixels are either black or white, corresponding to zeros or ones. Let us consider the image of size 8 by 8 by 1, where 1 stands for the fact that there is only one channel, one color, in this image. This is a picture of a zero. If we replace the color by their pixel values, we obtain this matrix, on which we can apply a convolution. Assume for now that the kernel has already been learned and is a 3 by 3 by 1 kernel defined in orange here. As a matter of fact, all learnable parameters in the slides are depicted in orange, so you can easily see that there is a difference between the input image, components are in black, they cannot be learned, and the kernel, components are in orange, they can be learned. But for now, let us forget about the learning phase, assume that we have this kernel, and compute the output of the convolution. The first element of the output is simply given by performing the term-by-term product between the kernel in orange and the area of the image in pink. These elements are then summed up, and the result is written in the corresponding area of the output. The second element is computed in the same way, with the same kernel, but the area of the input image, which is considered, has been changed. The area of interest has been shifted on the right. We repeat this operation until we have reached the end of the line. Then we can go back at the beginning of the line and shift the area to the bottom. The resulting output is given here. You can pause the video and take some time to ensure that you manage to compute all the components. The convolution can be summarized as this. By applying one kernel to one image, we have created a new image which we call a filter, an activation map, an output map, or more commonly, a feature map. Note that the output on the right has the shape of an image, which is not exactly of the same size as the original image. The kernel is composed of parameters that will be optimized during the network training. Nowadays, we often deal with colorful images, so we need to see how the previous convolution can be extended to colorful images. Colorful images are usually described with three channels: red, green, and blue. Each pixel can be decomposed into a red value, a green value, and a blue value, which means that the image is now a three-dimensional object. The image is now of size 8 by 8 by 3, the height, the width, and the depth. We can now consider a kernel of size 3 by 3 by 3, and the result of the convolution is obtained, as before, by considering the first area of interest in the three-dimensional image, multiplying this area by the kernel, element-wise, and summing up the results. As before, these values are stored in the feature map on the right. Note that here the values on the right are not accurate, since we did not consider specific values for the pixels in the input image. We could consider a kernel of a different size, height, width, or depth, but usually the depth of the kernel is the same as the depth of the input volume, here the image. Here the depth of the image is 3 channels, thus the kernel depth is equal to 3. Since we are now dealing with volumes, we will depict the convolution as this, where you can see that the learnable parameters, the kernel, are stored in a 3 by 3 by 3 volume. This representation is useful when we consider CNNs with many layers.